Friends, today we are going to discuss module 2, that is divide and conquer, right? So in previous class we have discussed brute force technique, and we learned that brute force technique is a straightforward approach to solve the problem. Here in divide and conquer strategy we are going to discuss how complex problem can be solved by dividing the problem into the sub problem. That is why it's called divide and conquer. First we are going to divide the problem into the sub problem, then finally we are going to merge solution to sub problem in order to get the original solution or complete solution for given problem. So that is why it is called divide and conquer. Under this divide and conquer we are going to discuss general method, general plan, then recurrence equations for divide and conquer, solving it using Master Theorem, and apart from this we are having some set of algorithm to discuss on the divide and conquer technique. That is binary search, max-min problem, merge sort and quick sort. Among that, merge sort, quick sort is a sorting technique, binary search is again searching technique, and min-max is only to find the minimum values or maximum value in the given the list of elements. So let us see that how you want to address this general method. As I said you that problem instances is divided into several smaller instances, ideally of same size, okay, or nearby size. Then smaller instances are solved often using recursion. It means most of the algorithms you are going to use recursive function, right? If necessary, solutions of smaller instances are combined to get original solutions. Let us see these pictorial representations. First is given problem is problem size of n, right? Now we have a sub problem size of n by 2. It means this problem size of n by 2 we have divided into two parts, right? That is, half of the part is left array, another half is called it right array. So left array size is n by 2, right array again size is n by 2. Or maybe if number of element in the list is odd number, say it is 9, then definitely when you are going to divide the arrays in two parts, we cannot keep it like the 4 and 4 equal size. Then what about 1, right? So basically we are going to divide the array. In one arrays will be having 4 and another arrays will having 5, right? Depends on how you are going to divide the array into two parts. Similarly, once problem is divided, right? Then we are going to find out solutions to this sub problem. So these sub problems will have some set of solutions. Another half of the problem will have another set of solutions. In order to get the solution to original problem, we are going to merge the two different solutions of half and half, and finally we will get solution to original problem, right? What is given it, right? Say as for example, if you are going to sort the list of 10 elements, right? So there are two ways. We can sort first 5 elements and last 5 elements, and finally we are going to merge it, right? And we will find what is the final sorted elements are. Similarly, if we are having set of elements, say we have 1, 2, 3, 4, 5, 6, 7, and we wanted to add these elements, right? We wanted to find the sum of these all elements. One way is there, you can write the for loop and you can start from here and go till here and find out the final sum. There is another way, person can go, they will add it like this, first 4 elements and last 3 elements, and finally you are going to find out solutions, half of the solutions, second half of the solutions, and finally we will get the solutions to original problem, that is called sum of all the elements. Now, why divide and conquer technique is needed, right? If you have other algorithm technique, remember that divide and conquer technique is required because if you have a complex problem, then there will be set of errors also in the first time, or while you are writing the programs or executing the programs, will be having some set of errors, right? Then because of some particular errors, we are not able to perform the task, right? Hence we need to go and debug that errors. It will take more time, because complete set of programs, say it is a 200 lines of code, then we need to find out proper errors and solve it. Rather doing that, we can divide the problem into the sub problems, and now we have some set of say first function is of 50, second function is of 100, third function is of 50 instructions. Then finding the errors or debugging the problems into sub problem is easier. So first is debugging is easier, right? Performing the task is easier, right? Then depends on the time complexity also. In some problems will have lesser complexity when you are going to divide the problem into the sub problems. So this is all about basic requirement of divide and conquer. Next is we are going to discuss, right, recurrence equations for divide and conquer. Remember that recurrence equations is very important, because as I mentioned that divide and conquer all the problem instances we are going to solve using recursive functions, right? And we have discussed in the previous module that recurrence equations as well, as for example t of n is equal to 2tn by 2 plus n, or t of n is equal to 2 of tn minus 1 plus 1 in the case of tower of y. So we have discussed this case. So let us see that in this, for divide and conquer, when you are dividing the problem into the sub problem, how you are going to write the recurrence equations and what is the use of that. So let us see that when you are talking about a problem size of n, then if you are dividing the array into two parts, right, say problem size of n is equal to 10. If you are dividing problem into two parts, then n by b will be give you the size of sub problems, where a is number of sub problems. What I said, this problem we are going to divide it into two parts. So definitely one sub problem will be 5 size, another sub problem will be 5 size. Can we write like this? If number of sub problem we are saying that 2, then size of sub problem will be n by b. N by b is nothing but 10 divided by 2 is equal to 5. So this is n by b is called size of sub problems, right? N by b is size of sub problems, while a, what we are talking about, number of sub problems. So here we can see that a and b are constant, where a is greater than or equal to 1 and b is greater than 1. Why? If b is 1, then what will happen? 10 divided by 1, what is the value? 10 divided by 1 is remain 10. We are not able to divide the problem into the sub problems, because each and every number is divisible by 1. Hence, b must be greater than 1, right? A can be greater than or equal to 1. Maybe we have only one sub problems, or we have many sub problems, right? As for example, we have discussed in previous chapter that factorial case, right? So there we are dividing the problems into just decrease by 1, right? So there we don't have multiple sub problems, we have a same sub problems, just decreasing the size by 1. Okay, let us see that. To write this in a standard form, T of n is called total time complexity, okay, for the given problem. Say any problem is given, total time complexity. Now, A is what? A, as I said you that, number of sub problem. N by b is size of sub problem. When you are writing the T of n by b, T of n by b is called time taken to perform half of the array. Time taken to perform half of the array. This is time taken to perform another half of the array. Multiply by a, size, number of sub problems. So 2 into time taken to perform half of the array. That is what concept is. Plus f of n. Now what is functional values of f of n? Remember that f of n is a function of n. Okay, f of n is a function of n. It can be, say, n to the power d. This value f of n can be n to the power d. Now what is a d? Here I bring some new terms called d. D is again variable. N to the power d. Now when d is equal to 0, we are getting just n. When d is equal to 1, value is n to the power 1 is remain n. When d is equal to 2, n square is quadratic. So we are getting based on this function of n, it can be, n to the power 0 is 1, or we have n when it is d is 1, it is n to the power 1 is n, d is 2, n square is n square. So you can see that constant 1, linear n square, like this. So these all are the function of n. Now what is use of this while you are writing in addition form, f of n? Remember that f of n is time taken to divide the arrays and time taken to merge the sub-solutions. For that reason we are writing here f of n. So you got the point now. A is number of sub-problem n by b is size of sub-problem, right? And f of n is time taken to divide and merge the solutions, right? That is why f of n function is. Now next, here we are going to discuss very important concepts called Master Theorem. Now why Master Theorem is? Why Master Theorem? Remember that Master Theorem is used to compute time complexity for given recurrence relations, right? Master Theorem is used to find the time complexity for the given recurrence relations. But what is the condition? Condition is Master Theorem you cannot apply for all the given recurrence relations. Your recurrence relations must be in the standard form. Your recurrence relations must be in the form of a t n by b plus f of n. If we can apply Master Theorem if recurrence relations is given in this standard form, what we learned in the previous topic, right? T of n is equal to a of t n by b plus f of n. Then only you can apply Master Theorem. Now let us see that. If that is the case, then there is three possibilities of time complexity, right? One, if a is less than b to the power d. Here is a, here is b, and here is function. We can write it in the form of n to the power d. If a is lesser than b power d, first compute this. If it is yes, then time complexity will be theta of n to the power d. If a is equal to b power d, in that case time complexity will be n to the power d log n base 2. If a is greater than b power d, then time complexity will be n to the power log a base b. It is theta of n to the power log a base b, right? When a is greater than b power d. So we have to remember this three things: a is lesser than b power d, a is equal to b power d, and a is greater than b power d. So most of the recurrence relations, when it is in a standard form, right, then we can apply Master Theorem. But remember that this Master Theorem cannot be applied in a tower von Weyl recurrence relations that we have discussed in the previous topic, right? If recurrence relation is in the form of some decrease by constant, right, this kind of things, we are not able to apply Master Theorem. Reason is it is not in the form of at n by b. It is just decrease by constant or whatever it is. If it is not in a, t, n by b, we are not going to apply Master Theorem for sure. Okay, right? So let us see that some problems based on Master Theorem. Okay, some example based on Master Theorem. Now you understood that what is Master Theorem? Master Theorem is to compute the time complexity. Apart from this, there are different methods of finding the time complexity. One is substitutions method, right? As you are saying that backward substitution method. Then you have recurrence tree method, right? But here in your syllabus, we have Master Theorem and backward substitution method. Let us see some examples based on Master Theorem. Okay, how to find out time complexity for the given given problem. So these all are the recurrence relations. So let us see that first example. Okay, first example. It is t of n is equal to 2t n by 2 plus n, right? Now, if you'll see that in this particular case, we are going to identify what is A. If you compare with the standard form, what is our standard form is T of n is at n by b plus n to the power d. So A is what? A is 2. Now, what is B value, friend? B is, you can see that n by b is 2. And what is the d value? D we can see, compare these parameters. So D is 1, so we can write it 1. Now, we are going to compare B power, we are going to compute from here B power D, right? We are going to compute B power D. What is B power D? B power D is nothing but B is 2, power 1 is 2. Now we are going to compare this, right? Whether A is lesser than B power D or A is greater than B power D, or A is equal to B power D. Hence, time constant will be T of n is equal to theta of n to the power D is D is 1 log n base 2. Based on previous concept, if A is equal to B power D, n power D log 2, no, base 2 n. So we are getting that time constant is T of n is equal to n to the power D log n base 2. So overall time constant of this problem is theta of n log n base 2. Done. Similarly, if you are going to solve second example, say it is the first, second, third, fourth, right? What is that? Here we have T of n is equal to T of n by 2 plus 1. Now compare with the standard form. Here A is constant, we don't have any values, hence it is A is 1, B is 2 and D is 1. 1 can be written as a n to the power 0. 1 can be written as a n to the power 0. So what is the D? D is 0. Hence B power D 2 power 0 is 1. Here we can see that it is again case of A is equal to B power D. A is equal to B power D. If A is equal to B power D, then time constant will be T of n is equal to theta of n to the power D. D is 0 log n base 2. Look, D is 0, hence n to the power D, n power 0 log n base 2. Can we simplify this? Yes. N power 0 becomes 1, hence we are getting log n base 2. So this is again time complexity of Master theorem. In this case, here we are getting n log n base 2, here we are getting n log base 2, right? Similarly, when you are dealing with third case, third is what? T of n is 90 n by 2 plus n square, 90 n by 2 plus n square. T of n is equal to 90 n by 2 plus n square. Now you can find out A. What is A? As all of you aware, A is 9. B, everyone is ready with the answer. B is 2. N is 2. Power term is, D is 2. Now we are going to compute B power D. So 2 power 2 is 4. 2 power 2 is 4. Now we are going to compare A and B power D. A is 9. B power D is 4. We can see that A is greater than B power D. If A is greater than B power D, hence we need to go and check which method you are going to apply, right? So as per that, it is n to the power log A base B. I will show you that. Look, if A is greater than B power D, then you are going to apply n to the power log A base B. Time constant will be T of n is equal to n to the power log A. What is the value of A, friend? 9. B. What is the value of B? B is 2. So hence this is the time constant of given problem, t of n is 90n by 2 plus n square is t of n is equal to theta of n log 9 base 2. If you are going to compute, it will give you n to the power 3 point something, right? 2 power 3 is 8, so it will give you 3 point something, n cube, n to the power 3 point something. Okay. Similarly, now we have one more problems, is t of n is t of n by 2 plus n square. So let us see that. Fourth example, t of n is equal to t of n by 2 plus n square. T of n by 2 plus n square. Okay. Again, same things. A is 1, B is 2, and D is 2. So we will compare B power D is 2 square is equal to 4. Now you are going to compare A and B power D. A is 1, B power D is 4. So you can see that A is less than B power D. It means what? A is less than B power D. In that case, time complexity will be theta of n to the power D. N to the power D. What is the value of D, friend? D is 2. So theta of n square. You can have a if A is less than B power D, time complexity theta of n to the power D. Done? So this is how we are going to solve a given problem using Master Theorem. Remember that recurrence relations sometimes they will give you, or sometimes based on the problems we are going to write the recurrence relations. Based on the given problems we are going to write the recurrence relations, right? And then you are going to solve it. See, as for example, we are going to discuss shortly binary search. Binary search. In this case, recurrence relations will be t of n is equal to t of n by 2 plus 1. Right? T of n is equal to t of n by 2 plus 1. And these problems are going to solve by backward substitutions method and Master Theorem. And we can see that in both the cases we are getting the same complexity, right? Called log n base 2. We will be getting log n base 2, theta of log n base 2. Similarly, when you are applying merge sort, right? Based on the algorithms, recurrence relations, we are going to write t of n is equal to 2t n by 2 plus n, and hence in this particular case time complexity will be n log n base 2. N log n base 2. You can compute it by applying the Master Theorem. Anyhow, you are going to solve it again in corresponding chapter, binary search, merge sort. Similarly, we have a quick sort, right? Again we will be having time complexity of n log n base 2. Friend, here we learned what is divide and conquer, general plan, how you are dividing the problem into the sub problems. Then we have discussed, right, what is the standard form of recurrence equations and how to apply Master Theorem in order to find out the time complexity, right? Remember that divide and conquer, wherever we required, right, problem is complex, you can apply it. Say as for example, in banking system you can see that people will have separate bundle of notes, 100 notes will be there. Okay, why 100 notes, why not 1000? Because when you are counting it, right, say we have 10,000 notes together, we are counting it, right, but one time you got confused, right, then again we have to restart counting from the beginning because we don't know, okay, where we did the mistake, right, and we don't have that count. So again we have to start from the beginning to find the proper number, right? But say if you have applied the divide and conquer technique, as in banking people used to do that, then what will happen? This in order of 10,000, wherever we have done the mistake, only that 100 we are going to recount it, remaining all it is there as it is. So in this way we can decrease our problem complexity, right? So it's not like that only we are going to apply divide and conquer in this particular case. Wherever we require that problem is complex, we need some technique, right, to solve a problem effectively and efficiently, you can apply for that. Okay, thank you very much for this class.